Hello everyone, my name is Priyanka Asnani and welcome to the course on model deployment using FastAPI. In this course, we will walk through the end-to-end process of deploying a machine learning model using a real-world classification problem as our guide. You will learn how to pre-process your data, prepare your model, build a robust API using FastAPI, package the model and API using Docker containers, and test the predictions interactively using Swagger UI. By the end of the course, you will have a fully functional production ready API that wraps around your classification model and the confidence to deploy your own models in real world scenarios. You have trained a great model. Now what? In the real world, a model is only valuable when it can make predictions in the production environment on live data and at scale. Deployment bridges the gap between data science and software engineering, turning a notebook experiment into a usable, accessible product. FastAPI is one of the fastest Python web frameworks that makes model deployment fast, simple, robust, and production ready. A trained model is only useful when it can make predictions in the real world. Deployment makes your model accessible via an API so it can serve real time predictions. This is where machine learning meets software engineering. Once your model is deployed, it's running in production, it helps business make data driven decisions in real time, and it also enables automation, scalability, and integration into your production systems. Flask and FastAPI are two widely used Python frameworks for building web APIs. While Flask is lightweight and simple, FastAPI is modern, high performant, and built for asynchronous processing. FastAPI is optimized for high performance by leveraging asynchronous processing to handle multiple requests concurrently and efficiently. FastAPI can handle tens of thousands of requests per second with low latency. FastAPI automatically validates incoming requests using Pydantic models, ensuring that data types and the required field are correct before reaching your code. This eliminates the need for manual validation and reduces the chances of runtime errors. FastAPI is significantly faster than Flask concurrent workloads, which is exactly what most ML model APIs deals with. So for serving ML models in production, FastAPI wins in terms of both speed and scalability. FastAPI automatically generates interactive API documentation using Swagger UI and Redoc. This makes it easy to explore, test, and share your endpoints without writing any extra code. FastAPI also uses type hints for validation to ensure that the inputs are the right type and structure without writing extra validation code. FastAPI also offers full support for asynchronous operations, making it ideal for IO bound tasks like database calls or model inference. This enables your API to handle multiple requests concurrently with high performance and efficiency. Let's say we are building a user API to manage all users in our system. Then we have these four CRUD operations that we can perform. CRUD stands for create, read, update, and delete. So if we have to perform a create operation, it would mean that we are trying to add a new user into the system. Read operation basically means that we are trying to retrieve details of a specific user by its ID. Update operation, we are trying to modify details of an existing user in our system. For instance, if we are trying to update the user's email, address, or phone number in the system. Delete operation basically just removes the user from the system. Let's say we have a public facing API that manages a catalog of programming languages and their metadata designed for developers, educators, or platform admins to browse, add, update, and delete programming languages info. Here is the list of different endpoints that we can define. The get API is the API that going to retrieve a list of all programming languages available in the system or the database. The post endpoint will allow the client to add a new programming language to the system's list. Get endpoint with the specific programming language ID will retrieve the detailed information of a specific programming language using its unique ID. The put endpoint updates the detail of a specific programming language with the given ID, and delete endpoint remove a specific programming language from the system. The HTTP status codes are returned as a part of response to indicate the result of an API call. These codes follow the standard ranges. Here is a breakdown of what each status group code means with examples of how they apply in FastAPI. The informational responses are the ones that are not commonly used in FastAPI. It is meant for interim responses only. The success responses indicate whether the request that the client sent was successful or not. Redirection responses indicates that server received a request, but there is a redirect to somewhere else. Client error codes are used to flag invalid and unauthorized request. Maybe the server couldn't find the page or the website that was being requested by the client. Server errors indicates that something went wrong on the server side. It means that client made a valid request, but the server failed to complete the request. So proper use of HTTP status codes in FastAPI ensures clear communication between client and server, making APIs easier to debug, monitor, and integrate. It also helps maintain standard predictable behavior for error handling and user experience.
Just a quick note, Analytics Vidhya has 100 plus free courses from beginner to advanced on topics like machine learning, generative AI, agents, etc. Complete with certification. Click the I button to explore now.
In this module, we will train a classification model using XGBoost on the US Census income dataset. The goal of this model is to predict whether a person earns more than 50K per year based on features like age, education, occupations, hours worked per week, and more. We will go through exploratory data analysis to understand the data, pre-processing steps such as handling categorical variables and creating new features, handling class imbalance, which is common in income prediction task, training an XGBoost model using cross-validation and hyperparameter tuning, evaluating the model using precision, recall, and F1 score. And by the end of this module, we will have a well-performing production-ready model that can be deployed and served by an API. The census income dataset contains 32K rows and 15 columns in total. Among these, the key numerical features include age, education, capital gain, capital loss, hours per week. These features provide important signals about a person's socioeconomic profile and the critical inputs for our income classification model. The dataset also includes several important categorical features that capture demographic and employment related attributes such as work class, education, marital status, occupation, relationship, race, sex, native country, and salary, which is the target outcome variable in this dataset. These features are essential for understanding patterns in income and must be encoded properly before training the machine learning model. In this project, we built a classification model to predict whether a person earns over 50K or less than 50K per year based on the demographic and economic features. These are high level steps we take towards building our income classification model. The first step in the process is loading and pre processing dataset, which involves using pandas to load the census income dataset, checking for missing values and removing any duplicates to avoid data redundancy, creating new features like has capital gain from features like capital gain and capital loss, and encoding categorical variables using label encoder. The next step is to train the XGBoost classifier on the pre-processed dataset. XGBoost is one of the most powerful and widely used algorithms for structured tabular data. Here is why. It offers a wide range of hyperparameters to optimize the model performance. XGBoost has its own built-in cross-validation method and supports easy integration with tools like grid search cross-validation and random search cross-validation. XGBoost automatically learns how to handle missing values, so there is no need for imputation when you're training the model. XGBoost model is highly modular, so it can be extended or combined with other algorithms very easily. It supports the customization for both classification and regression tasks. It provides feature importance scores, which is helpful for model interpretation and feature selection. It is also designed for speed, which supports parallel and distributed computing out of the box, and it's great for large data sets for fast training times. The final step in the process involves evaluating the model and choosing the best performing model based on metrics such as accuracy, precision, recall, and F1 score. To assess how well a model performs on unseen data, we use the following metrics. The first one is accuracy, which measures the ratio of correct predictions over all the predictions. It can be sometimes misleading with imbalanced data sets when we have overrepresentation of one class than the other in the data set. For example, we might get 90% accuracy when 90% of the samples in the dataset belong to one class. The second metric that we can use is precision. Precision measures how many of the predictions labeled as positive were actually correct. In other words, out of all the instances the model predicted as positive, how many truly belong to the positive class? This metric is useful when false positives are costly. For example, in spam detection use case, we might want to optimize for precision. The next metric that we should consider using is recall. It measures how many of the actual positive instances were correctly identified by the model. In other words, out of all the truly positive cases, how many did the model manage to catch correctly? This metric is important when missing a positive case is critical. For example, in disease detection cases, optimizing for recall becomes very important. The last metric that we can use for classification models to evaluate classification models is F1 score. F1 score is the harmonic mean of precision and recall. So it balances the trade off between the two. It is best used when you need to have a balanced view of precision and recall. In our income prediction task, we will focus on F1 score because our target classes are imbalanced and we care about both precision and recall. The system is designed to predict whether an individual earns more than 50K or less than 50K annually based on the demographic and employment related features. It is divided into two main components, the training pipeline and the inference pipeline. The training pipeline automates the end to end process of preparing and training a machine learning model using the census income dataset. It includes the following steps. The first step is the data validation, which ensures that the dataset is in the expected format. It checks for missing values, invalid types, duplicates, and schema mismatches. The second step in the process is data preparation, which handles missing values and duplicate entries. We perform feature engineering, encode categorical variables, and also split the data into training and test sets with stratification. The third step in the process is model training. It trains an XGBoost classification model and applies techniques like cross validation and class imbalance handling. The fourth step in the process is model evaluation, which evaluates the performance using precision, recall, and F1 score. It selects the best performing model based on the validation results. The last step in the training pipeline is saving the model artifact, this step typically involves serializing the trained model, label encoders, and metadata using Pickle, and it stores the artifacts in the model directory for deployment. The second component in this design is inference pipeline. The inference pipeline enables real-time predictions via a fast API application, which is containerized using Docker for portability and deployment. We first load the trained model artifacts and encoders from disk. We then write a Docker file which packages the API, model artifacts, and dependencies. We then build out an image that can be deployed locally or to the cloud. Finally, we deploy the model via a post endpoint that accepts user input, processes it through the train pipeline, and returns a prediction indicating whether the individual's income is greater than 50K or less than or equal to 50K. This function is a critical part of the pre-processing pipeline. This function ensures that the exact same transformations that were applied during training are also applied during inference, which is a critical for avoiding inconsistencies in the production environment. This function has six parameters: an input data frame containing both features and label, a list of columns that needs encoding, the name of the target column, which is salary, Boolean flag indicating whether we are training or doing the inference, encoders, a dictionary of pre-trained label encoder objects which will be used during inference, and a label encoder object for the label column. We then split the features and the label. So if a label is provided, it is separated from its features. We then During training, a label encoder is created and fitted for each categorical feature. These encoders are stored in a dictionary for reuse during inference. The label column is also encoded using label encoder, converting it into a binary format, 0 and 1. During inference, the same encoders from training are used to transform the categorical features. If a label is provided, during evaluation, it is also transformed using the saved label encoder. For the final step, the features are converted from a data frame to a NumPy array using two NumPy function that makes it compatible with most ML models and improve performance. This function returns the transformed features, encoded labels by the encoder's dictionary and the label encoder LB. This function ensures that the exact same transformations applied during training are also applied during inference, which is very critical for avoiding inconsistencies in production. We then have an apply label function. This function is used to convert the model's binary prediction into a more human readable label. The model predicts either 0 or 1 for each sample. 1 means that the model believes that individual earns more than 50K, and 0 means that the individual earns less than 50K. This function takes the binary prediction, which is usually as a NumPy array, and returns the corresponding string label. If the first prediction is 1, then it returns a string greater than 50K, and if it's 0, then it would return less than 50K. This file contains all the core logic for training, evaluating, saving, and loading your machine learning model. It's a critical part of the ML pipeline designed to keep model-related functions modular and reusable. The first function that we define in this file is train model. This function is responsible for training an XGBoost classifier using the provided training data. We handle class imbalance by calculating scale POS weight, which helps the model give appropriate attention to the minority class. In this case, the people earning greater than 50K is the minority class. This is important because the imbalanced datasets can bias predictions towards the majority class. We also handle hyperparameter tuning using grid search CV to perform a grid search over multiple combinations of hyperparameters like n estimators, max depth, learning rate, etc., with 5-fold cross-validation to find the best configuration. We then return the best model, which is using best estimator found during the grid search, which is ready to be used for inference. We then write a function, compute model metrics. This function computes evaluation metrics on the model prediction. We calculate three metrics, which is precision, which of all the positive predictions, how many were actually correct. Recall is of all the actual predictions, how many did we correctly predict. F1 score, it's a balanced score that combines precision and recall, specially used when the classes are imbalanced. We then return a tuple with precision recall F1 score, which we can log or display to track model performance. The inference function runs the trained model on the input data. It accepts the trained model and preprocessed input X. It internally calls model.predict to get the predictions. This is useful for both during evaluation as well as the real-time inference. We then save our model using save model function. This function actually serializes and saves the trained model or encoders to disk using Python pickle module. It first ensures that the directory exists, then writes the model to the specified path, and it then allows you to reuse some of the trained artifacts in the API or future workflows. The load model function deserializes a previously saved model or encoder. It attempts to load the file from the provided path. If successful, it returns the object, which is a trained XGBoost classifier. If the loading fails, it returns none. Common use is to load the models at the inference time inside the FastAPI application. Train model.py. This script handles the end-to-end model training for building a classification model to predict whether an individual's income is greater than 50K. The key steps include data loading, train test split, pre-processing, model training, and saving artifacts. It prepares all the essential components you need to serve your model using FastAPI and deploy it using Docker. We first load the pre-processed Census dataset using pandas. We confirm the dataset shape for verification. We then split the dataset into training and test subset. So training data is about 80% and test is about 20%. We also ensure that the stratification is done. Stratification ensures the label, which is the salary column, maintains the same distribution in both subsets, which is important in imbalanced classification. It saves the test data to this so that it can be reused later for evaluation and inference testing. We then define categorical features. These are the columns that require label encoding, since they are non-numeric features. We will also pass these to process data function to transform them into numeric values. This function separates the salary column. It encodes the categorical features using label encoder and then converts the label into a binary column using another label encoder. The function returns xtrain, which is the NumPy array of processed features, ytrain, which is a binary label vector, encoder, which is a dictionary of fitted encoders for categorical features, and then LB, which is the fitted label encoder for the target column. We then train the XGBoost classifier using grid search CV to find the best combination of hyperparameters. We apply scale POS weight to address the class imbalance. We then return the best model selected based on the F1 score using 5-fold cross-validation. We then save the trained model, which is a model.pickle file, label encoders for all the categorical features, and label encoder for the target variable into a model directory. So we basically save all the model artifacts into this model directory. These are essential for ensuring that inference uses the exact same transformations as training. Evaluation.py. The script performs evaluation of the trained model on the test set. It loads the saved model encoders, processes the test data, makes predictions, and calculates the final metrics, and saves the evaluation results in a JSON file. The script completes the ML lifecycle loop. It validates that your trained model performs well on real-world unseen dataset. It also ensures reproducibility using saved encoders and models. We first define all the file paths required to load the trained model artifacts and encoders, read in the test dataset, and save computed metrics. We then read the testdata.csv that was saved during the training pipeline. This contains 20% of the data unseen by the model during training. We load the trained XGBoost model, the categorical encoders, and the label encoders. These must match what was used in training to ensure consistency during evaluation. The test data set is passed to the same process function where training equal to false ensures that no fitting is done and the existing encoders are used. We get X-test and Y-test as the output. X-test is the feature transformed into the numerical format, and Y-test is the ground truth binary labels, which is 0 and 1. We then generate the predictions by applying the model on the test features to produce predictions. This is your model's best guess of whether income greater than 50K or not for each record. We then compute key performance metrics like precision, recall, and F1 score. We then save these evaluation metrics into a JSON file, which in this case is testmetrics.json, which is very useful for logging results, debugging, or displaying in a dashboard later. Hello, in this section, we will set up a FastAPI project to serve our trained machine learning model. We will walk through creating a FastAPI application to expose REST API endpoints. We will build a post endpoint service that accepts input and returns predictions. We will be loading our trained XGBoost classifier model so that it can run inferences in real time. And we will use Pydantic for input validation, ensuring that all incoming data is clean, structured, and matches the model expectations. By the end, you will have a working API that takes user input and returns a prediction, just like a production ML service. That will be used to create the FastAPI endpoint. We import OS, Pickle, Pandas, FastAPI, and Pydantic to create the API. We first load the functions from the data and model files that we created during training. These functions will be used to load the model artifacts, process the user input, and also the final predictions. We use OS module to dynamically set the current working directory and then construct the full paths to the model artifacts. If we see the model directory here, we have all the model artifacts stored in this directory. We are going to load the pre-trained encoder, which is used to transform categorical features, and then we are going to load the trained machine learning model, which is used for making predictions. The Pydantic data class defines the input format for incoming post request. Each feature is strongly typed using Python type hints. For instance, the feature age defines it's an integer field type, which means that it's only going to accept an integer input. Then we have working class, which is also a string field type. So that means it's only going to accept string input. We define these features, and then we are going to create a FastAPI app to handle the web request. We create a get endpoint, which returns a welcome message. It helps user know that the API is running and where to send the data. Then we create a post endpoint that accepts inputs via data model for model inference. We first take the data inputted by user and convert it into a dictionary. We then compute has capital gain feature with values 1 and 0. Since this is the feature we used to train our model, so we are going to create this feature for inference as well. We remove capital gain and capital loss since they were not used in training. We clean up the dictionary to turn it into a pandas data frame. And then we create the list of categorical features that we needed to encode for this inference. We then pass these categorical features as a parameter to the process data function, which is going to transform the incoming data into a format which is accepted by the model. Here, we need to transform all the categorical features using the encoder. And this is essential because we need to ensure consistency between the training and the inference. So we pass our categorical features and the user input into the process data function. And this function is going to return a new data processed array, which is the transformed array. And we are going to run model.predict on this transformed input. We then transform the prediction values 1 and 0 to the original labels before returning the final prediction. In this module, I will show you how to run FastAPI server locally and then test your API endpoint using the built-in Swagger UI interface. We will start by launching a server using Unicorn, and then we will walk through how to make a live API request directly from the browser without writing any client-side code. This is quick and practical way to validate your model is working end to end and your API endpoint is ready for real-time predictions. To start FastAPI server locally, we can use Unicorn command, Unicorn main app reload, and hit enter. Unicorn main app reload, where main:app tells the Unicorn to find the app object in the main.py file. The reload enables auto-reload. Auto-reload. The server restarts automatically whenever we do any code changes, which is perfect during development. The Swagger UI page will now show us these two endpoints, the get endpoint and the post endpoint. The get endpoint will show us this welcome message, and the post endpoint will accept the user input and return the predictions. We will then take this URL. When server is up and running, we go to the browser and hit this URL. This opens up Swagger UI. Swagger UI is a powerful built-in tool with FastAPI that lets you interact with your APIs visually. You can test your model predictions, validate inputs, and see results in real time, all from the browser. We can see our available endpoints, which is this get endpoint and the post endpoint. And we can also see the request and response formats and also the example payloads. Now, we will test our endpoints. So the first endpoint is this get endpoint that we are going to test. If we hit try it out and we hit execute, we are going to see our message, welcome to the income prediction API. And we also got a 200 response code, which means that our request worked and the server returned the result successfully. Now we are going to try our post endpoint, which already has an example payload. So if we try it out with this example payload, if we hit execute, and yes, we got the response from the API as the prediction as the income greater than 50K, which means that our input was valid, model made a prediction, and result was sent back to the client. Now, what happens if we make changes to any of these feature values? So, for example, we know that the input age can only accept integer values, but what if we give a string value to it? Let's see what happens. Let's see what happens when we provide a string value for the age input. And yes, we got a response code of 422 saying that our input should be a valid integer, and it was unable to parse the string as an integer. So that means we provided the input in the age as 33. It was a string input, and that's why we got the message saying that it wasn't a valid integer. So that's why our API failed and it wasn't able to return the result that was expected. So this is how we are going to test our endpoints from the browser. So we can test our endpoints from the browser, and we can also get instant feedback and results from the API. So this Swagger UI, Swagger tool is really helpful to test our endpoints and also validate our inputs. In this module, I will demonstrate how to Dockerize your FastAPI application so it can run in a portable self-contained container environment. We will start by writing a simple Docker file that packages your code and dependencies and all the model artifacts. Then we will build out a Docker image and use Docker run to launch our API inside a container and accessible on port 8000 just like before. This is a crucial step when you're preparing to deploy your model in real world production settings, whether it's a cloud platform or the local server. Start by writing a Docker file. So we start with a lightweight version of Python. The slim tag keeps image small by removing unnecessary tools. We then create and switch to a folder named app inside the container, and all subsequent commands will be run from here. We then bring our requirement.txt from the local project into the container, and then we install all the dependencies in the requirement.txt. This is how our requirement.txt looks. It contains all the packages that we'll be installing. We then copy all the remaining files like your app code, models, etc. from the local directory to the app inside the container. We then inform Docker container that the app will listen on port 8000. We then run the app using Unicorn. The Docker file gives us the lightweight reproducible environment to run FastAPI applications. Once we build the image and run a container, every model files to API code will be bundled and ready to serve predictions. We will now build the image using this command. The command builds our Docker image and gives it a custom name called FastAPI ML app. The no cache flag ensures that the image is being built fresh without any previous build steps. So we will hit enter, and it is now building the image. It will take few minutes. It is now installing all the packages from the requirements.txt. It may take few minutes before the image is ready. Okay, it looks like our image was built successfully, and now we are going to run the Docker container. So this Docker run command starts our FastAPI application inside the Docker container and masks it and makes it available on the local host 8000. Now we can test our API just like we did before. So now when we hit this URL on the browser, we will be able to see Swagger UI and we'll be able to test our endpoints. So the recap for this course is we set up a FastAPI application to serve a trained ML model. We built a post endpoint for model inference. We packaged everything into a Docker container, and then we ran the containerized API locally and tested it using Swagger UI. Once you are confident that everything works locally, then the next step is the cloud deployment. You can deploy this app on platforms like AWS using Elastic Container Service and Lambda. You can also use App Service or Google Cloud Run.